All right. Welcome, everybody. Let me just close out Spotify before, there we go. So we've reached the last lecture of COMP110, and we're going to be using it today to get a little bit more practice with a few things. A quick class writing exercise where we give you an example usage of a class and then have you try and write it, and I'm going to encourage you to do that by hand. Practice for the final exam. We're also going to be taking a look at recursion. A couple of quick announcements. So as a reminder, the last exercise of the semester, linked list utilities, is due tomorrow at midnight. The last day to hand this in will be Saturday. And I would encourage trying to wrap this up sooner than later. We'll have office hours through tomorrow at 5 p.m. 4 to 5 p.m. is our last set of office hours for the semester. I'm going to be hosting a review session on YouTube because it's after hours, and this will be at 7 p.m. This will be streamed and recorded. There will be a chance, and in fact, it will be primarily Q&A based, so please bring your questions. Happy to talk about anything. Today is the last day to apply to be a UTA for the fall, so I would encourage, if you're considering it, doing so. I'll try and get a link on, I don't think there's a link on the itinerary, but I'll try and add that later today. But it's definitely in what I think the most recent announcement that had all the things closing out the semester, and you can look for it there. Today is the last day to submit an exam conflict form through the registrar. I'll add the link for that on the itinerary as well, but if you just search for, final exam, conflict, because ours is a common hour exam, that means if you have a course that meets Tuesday, Thursday at 8 a.m., you're going to have a conflict. And because of that, that course will get the primary time slot, and the makeup is Sunday at 8 a.m., the day after our typical exam. So if you have a Tuesday, Thursday at 8 a.m., do be sure you submit that form today. All right. So the final exam, I want to talk a little bit about it. It's effectively a quiz and a half. It feels very much like a quiz, has the same kinds of problems on it, tries to be somewhat cumulative, so has, as best we can, rough equal representation of the concepts that we've covered, which means that, in fact, there are sections of it that are going to feel very lightweight because some of the early material you've been practicing this whole semester. There'll be a little bit of recursion, but about as much as we've seen this semester. There'll be a little bit of code writing, but you all are in a much better position for that this semester than in semesters prior because we've been practicing that every quiz this semester. And yeah, so the final is designed to be completed in 2 hours, but you'll have the full 3 hours, and some folks will take the full 3 hours, just being extra careful and diligent. That's totally fine. Some of you will finish probably in an hour, but it's really not meant to be a stress test on time, so it's not like 3 times the length of a normal quiz or anything like that, and it shouldn't feel like anything's coming out of left field because we've been practicing for this up until now. Any questions? So I will have seats assigned. You all will have seats assigned in here. The next section will have them in Genome 100. Those will be posted by Thursday, and I'll get an announcement up. Any questions on format? We can talk more about it if you have questions that come up at the review session. All right. Let's jump right into it with some code writing practice. So here, I'm going to encourage you to do this on paper. I'm giving you some example usage of how a class is used, a class named staff. We're constructing 2 staff objects. We're calling a method on each of them, and we see that there's different responses based on that method call, or output based on that method call. And we're not telling you exactly what how this greet method should be defined, but based on its usage, you should be able to infer that and try writing it on your own. So I'm going to pause here and go ahead and give you a few minutes to try writing the implementation of a class. So you're defining the class named staff based on this usage and description. Folks who are joining remotely, once you've finished, respond to the message in Course.Care. Another couple minutes on this. Two more minutes on this, and then we'll talk through it together. Twenty more seconds. All right. So when you see a prompt like this, we're looking for you to reason through how it's being used in order to understand how to implement the class. And some of the information that you need is given in the prompt, such as what specific attributes this class has. And those attributes, name and isCS, correspond to these arguments that we're constructing a new object with. So one of the first things I would do when trying to evaluate a problem like this and think through how do I design a class that meets these certain criteria, starting with the constructor and the attributes is a great place. So here we're telling you that these are the two attributes, and this is the name of the class, and then we know that we need to define a custom constructor that allows us to initialize those two attributes when we make a new object. The next thing that we see is a method call. And so being able to identify a method call is important. And this is a method that's called on an object of type staff. Its name is greet. And we can tell a few things from this usage. One, it's not going to have any parameters, right, other than the self parameter, which every method is going to need. And then two, it's not actually, the print is not going to happen here. This is going to actually return a string, right? Because we're returning that string and then we're printing out that string, which leads to this line of output. So based on that intuition, we can go ahead and start. So let's start with the class, and the class name is staff, right? And we know that we have these two attributes, so we define our attributes, and typically we always just define those first. So name is a string attribute, and isCS is a bool attribute, a Boolean property, oops. And then we have our constructor. So we know that we need to define a constructor that always begins with that's named init, and it's surrounded by two double underscores on each side. And that's going to have self, and then it's going to have a parameter for each of our attributes. So name is a str, and isCS is a bool. I'm kind of out of space here. So my colon's just below my parenthesis there, but I've got a colon at the end to say this is the end. And notice, because this is our constructor, effectively we aren't specifying a return type. It's implicitly going to evaluate to the class type, a reference to it. And our constructor is pretty straightforward, right? So self.name is assigned name. This is our classic pattern here, and self.isCS is assigned isCS. We don't need a return statement. We're sort of good to go here, right? So this is our constructor. It gives us the ability to set up these attributes and initialize an object with these two parameters. So we know that we now know that we've effectively checked off, this piece of functionality that we need to do. And now we can turn our eyes towards the greet method. But before I do that, any questions on attributes, constructor, anything like that? Yep.
Does your ever specify that self is like class or staff?
Good question. So do you ever need to specify something like self is staff? So Python will actually prevent you from doing so because it's always implicitly that. Self is always going to be the same type as the class that you're defining this method or constructor in this case, the constructor. And so that's why we don't type it there. Good question. But yeah, it is always going to be that type, and that is important to understand. That the type, if we asked you what is the type of self, the type of self is staff. All right. So let's think about this method. So we see two uses of this method, and we see two objects here, right? So there's another object being created, staff with the name of Mara, and isCS of false. And here's where we're asking you to infer some behavior, right? So, okay, when we print, or when we call the greet method, it's returning a string where it says, hello, I'm Chris in CS. Whereas when we call the greet method on an object whose isCS is false, and we can kind of infer that because that's really the only difference that could be other than the name, hello, I'm Mara, not in CS. So we know we're going to have a conditional behavior in here. We know that this is a method that's going to need to return a string. It's a method that doesn't have any other parameters besides self. So let's try setting up the skeleton of this. So we set up the signature line, def. Greet is the name. And our only parameter is the self parameter. We define this on methods. And this is a function that returns a string, right, ultimately. So we still have more work to do, right? We haven't implemented this yet. And one of the things I'll say, when you're writing code on the final, you don't have to add a doc string. If you want to, that's great. But we're not necessarily looking for that because we're mostly looking towards functionality. So that's why I'm not writing doc strings in this example. So we need an if, right? So we can test if self dot isCS, and if so, we can return. And this is going to be an f string that's going to span 2 lines of my slide here. F string of hello, I'm, and then this is where I'm going to span 2 lines. Self.name, I'm actually going to span more than 2 lines here. If you want to put ellipses or something, if you run out of space on a given line, on paper I think you'll have more room. If you run out of space on a line and you just want to do some ellipses, and be sure that it's obvious that you're wrapping around, that's totally fine. So self.name, and I'm going to need to put some more ellipses. And because this is in CS, I can write in CS here. All right. Else, I can return an F string that's very similar, but it'll say not in CS instead, right? And there are other ways that you could have gone about this, right? We could have concatenated a string and only had the difference be in the concatenation of in CS or not in CS, because the rest of this is otherwise the same. This is sort of the most direct way of doing it. Self.name. And not in CS. All right, so I apologize for that getting small, but hopefully that makes sense. One of the things that hopefully, actually I'll take questions. Yep. So this is a great question. The question is, for this if statement, why do we not have to substitute? Why do we not write this as something like if self.isCS is equal to true? Right? So if we go back to the early days of 110, where we're learning about these types of equality expressions, what do we, so if self.cs is true, so let's imagine we substitute true here. What does this evaluate to? It evaluates to true, right? Well, I want to convince you that if we just write if self.isCS, because isCS is a Boolean type, when we evaluate this, if this is true, we would substitute true here, and it would be if true, and we would go into the then block. But if isCS, so in the case of Mara, when we call this method on Mara and we looked up what is isCS and this evaluates to if false, well then at that point we would go to the else block. And so it's kind of redundant to say if a Boolean is equal to true, because the Boolean itself is either true or false. Does that help? Yep. Yeah, so this test can, whatever expression you have here, once it evaluates, that's exactly right. If that evaluates to false, you go to the else. If it evaluates to true, you go to the then. And what's neat about variables or attributes that are Booleans is that they're always going to evaluate to either true or false themselves. And so it's kind of self-explanatory once you, it stands for itself when you reach this point. Other questions? Yep.
Will we get points off on the final if we did include the if self.isCS?
No. So we're not going to be looking for that level of style. I'm wanting to demonstrate. So the question was, if you did do is yes is equal to true, would you get points off? No. I would encourage being comfortable with this pattern if it came up, because it is, once you are comfortable with it, I think becoming comfortable with this makes you a little bit more comfortable with how exactly that expression, that test expression gets evaluated. Other questions? All right. So one of the other possible extensions you could imagine here is that maybe this method had some parameters or took some arguments and passed them into parameters, so you might need to worry about that. If we use this in a different kind of expression, you would maybe need to think about the return type a little bit more specifically. Here it's pretty obvious this is returning a string. Yeah, so this is an example of the type of exercise you might expect with code writing, where we're asking you to define a class based on some usage. All right. So for this next diagram, I want to step through this one together to give you a sense of something that's a little bit funny. We haven't looked at a recursive procedure yet, but we're going to look at this recursive procedure together. And then I'm going to turn you to take on something that's very similar, but not quite the same. So let's have a globals frame. Globals is going to have a branch function. That's a function on lines 1 through 12. Okay. On line 15, we see a variable being declared length. That's 8.0, and angle, which is 90.0. All right. And then we reach a call to branch, so we're going to have some work to do. Before we actually look into branch, I'm going to ask you to look at this function implementation and think through whether you imagine it's recursive or not. Is this a recursive function? So in 10 more seconds, I'll ask folks who think this is a recursive function to raise their hand who are in class, or to respond. I'll make a message if this is a recursive function. Respond to this message, all right? So if it's a recursive function, raise your hand. All right, I see a lot of hands. Absolutely it is. And I'm glad that you're recognizing that when you see a function call within a function that's calling itself, you've got recursion. This one's a little bit funny because the base case is strange, different than we've seen before. Well, it's funny for two reasons. One, we don't have a return statement here. This is a procedure, so it implicitly returns none when we reach the end of the function. But we're also defining this base case in a strange way. And maybe a little bit later I'll talk about how we could define this in a different way, but I always do think while you're still getting comfortable with recursion, it is nice to specify base cases explicitly, which is what we're doing here. Right? So in the base case, we're just doing nothing. Python has this really cool ellipses syntax that you can actually write that just means no operation is what we call it in computer science, or no op, but means do nothing. Like this is just and so you can write these ellipses in function definitions or in places where you're going to come back to, and it's kind of handy at times. So this is a valid program, but let's jump right into it. So I'm going to set up, there's not a lot happening in the heap, so I'm going to give myself a lot of output room. And this will be important on the next one that you all are diagramming as well. All right. So we set up a call to branch, and so let's set up a frame for this. Branch. The return address is line 17, and L, which is short for length. I'm doing that so that we don't have to write quite as much on our diagram, is 8 initially. And A, the angle, is 90. Right? So we jump in, and we print branch. Right? So branch is our first line of output. And then we print ang, short for angle, and substitute in A, which is 90. And then we fill in forward, which is length 8.0. All right? So we finished those print statements at the top, and now we are testing, is length L less than 4? No, it's not. So we're going to go into the else, and here's where we're going to reach a recursive call. Notice that at the point we reach the recursive call, we're still going to, when this finishes, we're still going to have more work to do in this particular frame, but we can't do that work yet until we go do the work of making this recursive call. So let's set up a frame for this branch. So this call to branch is on line 9, and it has an L of the current L, which is 8, times 0.5. So half of L is going to be 4.0. Right? And A, the angle, is we're adding 45 to it. So 135 is the A of the second frame. Okay? So we've established this frame. And now our current frame is the one whose L is 4 and A is 135. So we're ready to jump back into this new function call starting from the top. All right? So we jump back to the top, and we print branch again. And then we print angle A, which is 135. And then we print forward L, which is 4.0. And then we test if L is less than 4.0. That's still false, right? So we haven't reached our base case yet. We go to the else branch. And we set up a new frame. Branch, return address is line 9 again. And this time around, L is 4.0 multiplied by 0.5, or half of 4. So that's going to be 2.0. And A is 135 plus 45. So that's 180. All right. We've set up that frame. We're going to change our current frame to be this one now that we've fully set it up, and we're going to jump and start this frame's evaluation of the function from the very top. What do? Well, we print branch again. And then we print ang A, so ang in the current frame is 180. And forward is 2. All right? And here's where we reach our base case. Right? So if L in the current frame we're working in is 2, is less than 4, we're going to do nothing. So we're going to go into the then branch, we do nothing, and then we skip past the else, right? And now we're going to print ang again, but plus 180. All right, so now we're printing ang 360, right? And then forward L, which is 2.0. All right. And when we reach line 13, we see that it's blank, and this is the end of the function definition, and we're still in this frame, right? So I haven't finished out this frame. But before we start returning, any questions on how we got to this stage of the evaluation? So there's a question from online that I think is very good, which is, why do we go back up to the function definition and not just the if-else loop? And there are two things I want to point out here. First, I want you to be very careful with the difference between if-else, which is a conditional statement, and is only ever going to be evaluated, we're going to start at the top of this. If it's true, we'll go to the then block. If it's false, we'll go to the else block, and then we'll continue on. We're never going to jump back to the top of an if-else block. If this were a while loop, it would actually be a loop, right? So while loops are loops, for loops are loops. If then else is a conditional, and it doesn't have any looping involved in it. So there's a fundamental difference there. But the next question, the fundamental question here is, why don't we jump up here? Why do we jump all the way back up? And what's important to recognize is, like, imagine this, instead of this being a function called a branch, imagine this is a function called some other function named, say, foo. We know that we would jump into that foo function and start it from the top. This is a function call. That's what we've been doing ever since we started looking at functions. This is no different than any other function call. It just feels a little funny because we're talking about calling the same function. So whenever we call a function, after we set up the frame, we always go to the start of its definition and start working line by line from there. But our frame values are, we've established a new frame and we're working in that frame. And so that's why we didn't jump to, or that's why we jumped up to the top of the function definition. Other questions? All right. So we've reached the end of this branch function with this frame, right? And we know this is our current frame because it's the lowest that is yet to return. And in just a moment, in the next tracing, you're going to see that this will be a little bit different. Or that notion that our current frame is the lowest that is yet to return will become more important to keep in mind. But here, so our return value is going to be none, right? In fact, all these return values are going to be none, but we can't just draw a none here and then start over because we still have more work to do. So we return none, and we go back to line 9, right? That was our return address. So that return address is telling us we go back to this line, and this was the line we just finished, right? We're returning none, so this line is done. We don't have anything else to do. We called this function. We finished evaluating it, returned none, so let's carry on. So what happens after that function call? Well, that's when we reach line 11, but now notice that our current frame is this one, where L is 4 and A is 135. So when we reach this print statement, I'm going to have to like wrap my output around. We print ang, and then A plus 180. Well, A in this frame is 135. So I'm going to do the embarrassing thing here. Doing math in front of people is very stressful. And 315 is our angle that gets printed out here. And then forward is 2, right? Or sorry, forward is 4. So forward, and we're substituting L. L in our current frame is this one. This is the frame we're working in. So forward, L is 4.0. And technically that should have been 315.0. All right? So now we've reached the end of this frame, and we return none. All right? Where are we returning none to? Well, that's what our return address is keeping track of. We're going back to line 9. So we're going back to this line. And we just finished this line. But now notice our current frame, the one that's yet to return that we're working in, is this frame for branch, where L is 8 and A is 90. All right? So we just finished that line, and now we reach the print statement for ang again. Ang is A plus 180, so A is currently 90. 90 plus 180 is 270. And forward is 8.0. All right? Let me draw this arrow. And so we finish this out. Well, not quite, because we reached the end of this branch, and now we need to return none. But notice, we're returning to line 17, and line 17 was back in globals. There's nothing in our program that comes after line 17, and so now at this point, our program is done. Any other questions? Yep? Why don't we deal with heap that much? So in this example, we just have function calls so there's no objects, there's no lists, there's no dictionaries. And because of that, the call stack is just for keeping track of what's going on in a function. And what we're seeing here is a function who only uses local, simple types like float. And that's why we're only seeing things in the stack other than the function definition. Good question. There's another question that's coming from online. Could we write the same function without having this base case specified in this way and sort of flip this to say if L is greater than or equal to 4.0, then do branch and not do the else? And yes, we'll try this out. Hopefully we should be able to have time to try this out when we get a little bit closer to the end. All right. Other questions on this example? All right. For this next example, I actually want to change one of the inputs here to be 4.0 instead of 8.0. And I want to give you all a moment to try processing this instead. Leave plenty of room for output, and you won't need room on the heap here. For folks who are joining online, if you'll respond to the Course.Care message, react to it, once you're done. Once you finish, try imagining how different this might be if you called this with 8.0 or 16.0. And visualize the beauty. Two more minutes on this, and then we'll work through it together. One more minute. If you're done, do try and visualize the beauty of what you're establishing here. All right, let's work through this together. Oops. One sec. I gotta duplicate. Okay. So we've got this function, and it's interesting. It's different from the other recursive functions we've seen because there are two recursive function calls happening within this frame. And I need to change this so that it matches what you all were supposed to do. So this was 4.0. All right. So we set up globals, and it's got our branch. And this is a function. I'm not even going to write the lines in. I want to move a little bit quickly through this because the important part is when we get to that double function or that double recursive function call. So length is 4.0. Angle is initially 90. And great, we're ready to set up this frame, right? So our frame is for branch, and the call happens on line 18. And our L parameter is 4.0, and our A parameter is 90.0. All right, and I'm once again going to set up, just give myself a lot of space here for output. Okay, so we go in, we hit this branch. Okay. And if we looked at our output for the previous function definition, we know that every time we see branch, that means there's at least one recursive call happening. And so that's actually going to map one-to-one with the number of frames that we set up in this function, in this recursive function call. Then we reach ang, so this print is ang a, which is 90. And then L is the length for forward, and forward is 4.0. All right? And then we reach this if statement. So if L is less than 4.0, we do nothing. Well, L is 4.0, so this is when we hit the else. And oh no, we see 2 recursive function calls. The good news is we only need to process these one at a time and just keep following our rules. So this first one is going to set up a new frame for branch. And L is going to be 2.0. A is going to be 135.0, right? And our return address here is line 9, right? And this will be important in this one. So we're going to come back to line 9 once we're done with this. So we set up this frame. We jump to the top. We print branch again. This time we print ang 135 and forward 2, right? And here we reach this if. We're done. L is less than 4.0. That's true. So we're done with this one. So let's go ahead and print, ang is 135 plus 180. What did I say that was? 315. All right. And forward is still 2.0. All right. So we're done with that. And we return. So we return nothing. And we're going back to line 9. So we just finished line 9. And our current frame is this one. All right. So then we reach this call to branch again. And this is the first time we're seeing this. But this is possible. Why not? We can have a function call wherever we want. Why not have another recursive function call here? So we add a recursive function call here. This time around, notice that the return address is different. It's line 10. And our L this time is a quarter of the L in our current frame. So that's 4. So 1.0 would be L. It's a quarter of 4. And A is going to be 90 minus 45. So that'll be just 45.0. All right. We set up our parameters. So we're ready to jump in, and we go back to the top, and we print branch. All right. We go to angle, this time around, 45, and length, or forward, I should say, forward is 1.0. All right. We're still here. We test. Well, our L is 1, so it is less than 4, so we do nothing. And then we print, this angle again, which is 235, no, 225, if I could add. 225, and L is forward 1.0. All right, and then I'm just going to continue on at the top. So here's where things continue to be a little bit interesting. So we return none, and we return to line 10, all right? So this is where we return none to, but what is our active frame now? Well, it's the lowest frame on the stack that is yet to return. So we return to this frame where L was 4 and A was 90. And we just finished line 10. That function call is what we just processed. So now we finish this out, and we print ang of 90 plus 180, so 270, and forward of L, which is 4.0. All right, we reach the end of that function call, so we're done, and our program is done. Questions on what we're seeing here? Do you all see the beauty of this? No? It's beautiful. So how many recursive function calls do we have? So, or how many function calls a branch? Branch was 1, 2, 3. If you try imagining what would happen if we called this with 8, it'd be even crazier, right? I don't know, I'm a little disappointed. I guess I'm not inspiring enough for you all to see the beauty in this. But maybe it's just that point in the semester where we need to take a moment to close our eyes. And for those of you who are joining online, I want you to close your eyes as well. I want you to visualize being in a forest. Are your eyes closed? Well, I hope so. And I want you to take a deep breath. It's the end of the semester. We're learning about recursion, one of the most beautiful forces in the universe. Exhale. Inhale. And we're about to go into finals, and everything will be okay. Exhale. I'm very bad at leading breath exercises. Inhale. I want you to imagine a tree, just like you saw a beautiful, happy little tree. And since you couldn't see it before, we're going to work through this together. All right? And hopefully someone else will be able to inspire you so that you can understand the beauty of what we just did. But what I'm going to ask you to do is actually get out VS Code. Oh, yes, there are no happy accidents, or there are no mistakes, just happy little accidents. And so you might know this famous YouTube star, Bob Ross. And what we're about to do is paint a happy little tree together. And I'm going to explain the intuition with you, but go ahead and get out your VS Code. And we're going to start with what you're seeing on the screen here. And so I'll ask you to open a new Python program named tree.py. This is very similar, or it will be very similar to what we just sort of traced through together recursively, that beautiful, beautiful recursion you just worked on. And this time around, we're going to be using our old friend, the turtle, to do a little art together. So I'm going to give you a moment to catch up here. And what I'll point out is we're using the turtle library a little bit differently than you all did. We're effectively importing the turtle library as a global named t, and then we can give our instructions to that t. So t.forward, t.setHeading, which changes the angle, t.pan up, and we can move the turtle around the screen. And this is setting up our canvas. And if you were to try evaluating this program, you would see that you have a beautiful straight line being drawn, and that's about it. So we've got two functions defined here, one named tree and the other named branch. And we're about to make this branch function work very similarly to what we were just tracing in the environment diagram. But I want to talk about just what's happening at the very end of this program. So we're starting directly from globals. We're speeding up this turtle a little bit, setting its speed to 5. We're saying start this tree at the origin. And the tree function has 2 parameters, right? So we lift our pen up, and we move to whatever x, y that we've established as those parameters, and then we put the pen back down. So we're about to make a beautiful ink stroke on our canvas with our friend the turtle. We set up some constants. We're trying to draw a tree, so we may as well specify the length of a tree's trunk as 100 units, And we're establishing up is 90 degrees. And then we draw our branch. And so what do? Well, we're painting together. So we stroke out up the branch and then back down. We set our heading to 100, or sorry, we set our heading to 90, which is straight up. We move forward by 100, and then we set our heading to 90 plus 180, which is setting us right back in the direction we came from, and move back down. So if I try and run this, wow, look at that beautiful tree. But we'd like this tree to grow, right? So how can we add some additional life to this tree? Well, with some recursion, right? So if our length is, say, less than 3.0, we're going to do nothing. This is the base case, right? Else, what are we going to do? Well, what happens when we branch in a tree? We're going to branch. Let me see. I'm going to scroll this so that hopefully as much of this as I can fit will be here. And when we branch, we've reached the top of our trunk at this point. What do we want to do? Well, the next branch, we probably want to be a little bit shorter, right? Because our base case depends on this length being less than some amount. So I don't know. We can be artists here and multiply by, say, 65%. We can play around with these magic numbers in just a little bit. Well, branch doesn't continue in the same angle, right? It kind of turns a little bit. So why don't we increase our angle by a little bit? And this is in degrees, so I don't know, perhaps our angle increases by 25 degrees. All right. Cool. We've got recursion, what we just traced out. This is getting pretty close to it. This is like the very first sample listing. So let's see what our beautiful tree looks like. Oh, wow. It leans a little bit to the left. But it looks like something. So the problem is we're not drawing any branches to the right. Right? So what we just did, and what you just traced through, that beautiful code listing you just traced through, add a branch to the right. So we can make the length, I don't know, maybe our right branches are a little bit shorter, 0.60. And instead of increasing the angle, we can decrease the angle. That'll move us towards the right instead. And maybe we choose like 20.0. I don't know. And so notice now, every time we branch, when we're in the recursive case, we're going to branch 2 more times. And if we're still in the recursive case, each of those branches will branch 2 more times. So let's see what our tree looks like now. Wow, our turtle's doing a lot of work here. Each time you see that turtle changing direction, that's the end or the beginning of a new recursive function call that it's processing, right? This is a little tedious to watch slowly draw, but you can see that, okay, we're making progress on this tree. Let's try speeding it up a little bit. So if we set a speed of 0, that's as fast as we can draw it while we're still seeing each of the individual steps. And I'll try and keep as much here again as I can. And we watch it do its thing again. And so you'll notice that we've got this tree that's coming to life through the beauty and the magic of recursion. That beautiful code listing. And if you were to trace out those print statements that you saw in your environment diagrams and try and follow the same steps that this turtle is taking on a pencil and paper, you would see that that's the start of a tree. Luckily, those diagrams didn't contain multiple thousands or multiple hundreds of recursive function calls. And so that's pretty cool. So one of the things that's really interesting and one of the fascinating applications of recursion is that you can work with tree art. This is related to the idea of fractals. But you can also work with tree data structures. So we've seen linked lists that have nodes connected in one direction. But you can imagine having a linked list that has another node, maybe a left and a right, that represent, and you can start to build trees, and you could use recursion to process those data structures. Well, I don't know, we could have a little bit more fun with this, and we're supposed to be artists here, right? So one of the things we could do is make it so that we can draw trees in other places. But before we do that, we should probably make this a little bit more immediate. So with a little bit more magic, we can say t.tracer 0, 0. You might remember this from your project. So this only updates when you call update, t.update. All right? And so this will make our recursion even faster, or our visualization almost instantaneous. Because what we're going to do, the other thing we're going to do is, I'm going to scroll up just a little bit more. And in our tree function, I'm going to add a line that is t.update. All right? And Python wants me to have 2 spaces after the end of a line before a comment on the same line, so I'm going to do that. And so all this is doing is nothing really fundamentally important, but it should make our, yep, boom, look at that. And I want you to appreciate that the instantaneous, let me try making this a little bit larger actually too. So maybe our trunk is 150 instead. So we start with a longer trunk, that means we're gonna have more branches. And that's starting to look pretty neat. I want you to appreciate that what we just did by hand with all those frames and setting up our local parameters and things like that, that's happening as soon as we hit play, or as soon as we started this function, or this program, and boom, it showed up on our screen. It had already carried out all of that, and you start to get a feel for just how fast these our computers are. The other thing I want to point out is that you can actually see the recursion here visualized, right? Every one of these lines represents a recursive function call that's being evaluated by your computer, by Python. And so we can also see how deep the stack gets. If you imagine we erased our stack frames after they returned, we could see how deep our stack gets. And this is one of the ways that we can kind of get the sense that, oh, we can actually process quite significant amounts a significant amount of frames without going too deep on the stack, thanks to this treeing nature. So, we're supposed to be artists, so let's give ourselves the ability to draw our own trees. So rather than on line 28, we just draw a tree at 0, 0, we can do something kind of neat. We can ask the screen, so we can ask the turtle for the screen, which is an object representing our window, and this has the ability to respond to click events. And what we're saying here is we're saying, hey, screen, when I click on you, I want you to call the tree function, right? And whenever you click somewhere, the function that you give it is given an offset, an XY of where you clicked. And so now, if we run our program, it'll initially have a beautiful blank canvas. And, oops, when you click, we can draw a beautiful little forest together. And you could imagine doing some other things, like adding some randomization, so your trees aren't all exactly the same, because we know in nature that's not true. Sure, we can just do this really quickly. We've got a couple minutes left. So let's try adding a little bit of randomization here. So from random, import random. Random, the function in the random module, will give us back a random floating point value between 0 and 1. And so we can, I don't know, set up another variable named nature that is a float, and it is random multiplied by, say, 0.3. So 30%. Between 0 and 30% is the difference in tree trunk size. So maybe rather than 0.65 on that first branch, let's try something like 0.55 plus nature. Right? And so we're adding nature into the equation. I have no idea what this is going to look like. I've never tried this before. It could be a mangled tree, but let's see what happens. It's subtle, But if we were to look very closely, we would see these are different from one another. If we increase the randomization here to say 0.5 instead and tried this again, it would be a little bit less subtle. So this is changing the length, but we could also change the angle. So rather than plus 25, we could do 25 multiplied by nature, right? So anywhere between, yeah. So let's see what this looks like. Got some funky looking trees here. They're blowing in the wind, right? It's a windy day out on the beach. You can imagine yeah, these are some happy little trees blowing in one direction. But you can imagine that many things happen in this way, right? So the beauty that you all traced before is exactly what's happening here to bring these trees to life on the stack and what the computer's doing behind the scenes. So I want to close out. I've got a couple more slides. At the beginning of the semester, we talked about the fundamental pattern, okay? And we said most of what we do in computer science involves some inputs being fed into some kind of algorithm, and that results in some outcome. And when we're talking about functions, that's a return value. When we're talking about print statements, it's output on the machine. And this all happens within some environment where maybe we're reading files into our algorithm as part of a data analysis, or maybe we're printing things out to it. Well, you've been a fundamental part of this pattern this semester, right? Taking COMP110. We've been pushing you incredibly hard. Exercises nearly every week, lectures, readings, quizzes. This algorithm that we've established has the intent, it doesn't have the intent of being operated in a pandemic, but the environment is the pandemic, and it has the intent of making you into a programmer and a data scientist. And what I think you can be very proud of at this moment is that you can call yourself a programmer. You've spent a lot of time in front of the computer writing programs that are non-trivial and doing some elementary data science. So I want to give a couple thanks to a few people. We've got one TA here today, but the others, I can show them this recording, so a round of applause for our team. This team, and let me get this camera out of the way so that everything can actually be seen here. Couldn't have done it without them, obviously. I know many of you have grown close with them in office hours and tutoring, and this course wouldn't be possible without their help. Once again, we do have a lot of graduating seniors this year, so if you're interested in joining the team next fall, I would encourage you to consider applying, and I'll add that link to the homepage. But yeah, this team really has done it all, from running Hack 110 to helping in lecture, holding office hours, tutoring, review sessions, and they're a fantastic group that I appreciate the heck out of, and I hope you do too. But there's one more group that I want to give a special thanks to, and that's you all. You all have really put up with a really strange, difficult semester with waves of COVID coming through at the beginning, and now we're going through one right now. You've endured a lot on campus, the highs of a national championship almost run, to the lows of lots of your friends being ill and things like that. And meanwhile, you've kept up the really high degree of work that we expect in this course, the time spent crying / getting jubilant and euphoric when your program runs and you see the output that you expect. So yeah, thank you all for an incredible semester, and round of applause to you all. And with that, we'll see you back here on Saturday. All right, welcome back, everybody. Happy COMP110 LDoc. I know LDoc isn't technically until tomorrow, but this is our last lecture together. Hold tight. There's test 1, 2, 3. Okay, I think we're, yeah. Just want to be sure sound is going through on stream. So today we'll be getting some practice looking towards the final exam and a couple of quick announcements on that front. Final exercise of the semester due tomorrow. Last day to hand this in late would be on Saturday, so I would encourage trying to get this in. We'll have office hours through tomorrow at 5 p.m. We close early on LDoc because LDoc, especially spring LDoc, is such a joyous day on the campus. No one should be doing work after 5 p.m. So you should get yours handed in before 5 p.m. tomorrow and enjoy your LDoc. I'll be doing a review session at 7 on Thursday, which is the reading day, and this will be live streamed and recorded. I'll be doing this off campus, so it'll be streamed remotely. We'll be doing Q&A, come with questions. Happy to talk about anything you have questions about. Today is the last day to apply to be a COMP110 UTA in the fall. I'll get a link posted on the course site after class today, but there should be a link in the announcements on Sakai as well. I would encourage, if you're thinking about it, to throw in an application if you think you'd have fun teaching other people about computer science and working with the course. The final exam is this Saturday in Genome 100 for you all. So when I assign seats, it will specifically say for you all which seat in Genome you'll be headed to. But you will be in Genome G100, which is a pretty lavish, large room on campus if you've never been there. Those seats will go up on Postum on Thursday. Today is the last day to submit a final exam conflict form. So because we have a common hour exam, which means both sections are taking the exam at the same time, the only way to do that is to have it potentially conflict with another exam. So if you have a Tuesday, Thursday class that meets at 8 a.m., that would mean that you would have a conflict, and the class that you're regularly scheduled for takes precedence if you read the registrar's calendar on this. So if you have a Tuesday, Thursday, 8 a.m. exam that's also at Saturday, 8 a.m., you should fill out this form, and what that means is you'll take the alternative conflict exam on Sunday at 8 a.m. instead. All right. So there's been some questions on the format of the final, what to expect. I've talked a little bit about this, but effectively you can expect that it's about a quiz and a half in length. It tries to be reasonably representative of the whole semester. And what that means is some of the things will feel pretty straightforward because at this point you're very comfortable with early semester concepts such as if-then statements, loops, variables. The weighting of concepts tries to be relative to the weighting of the amount of time we've spent on things. So there will be some recursion, but it's weighted about as much time as we've spent on recursion, which is the last few weeks, right? So it won't be as heavy as the other fundamentals. The final is designed to be completed in 2 hours. I expect some folks will take all 3 hours. That's common, just to be extra careful. Some people will be done in an hour. That's totally fine too. But yeah, we're hoping that folks are able to get through it and have had time to think about every problem with a reasonable amount of depth before the 2-hour mark. Yeah, and format-wise, it should feel very, very similar to a quiz. You don't need a Scantron or anything like that. It'll be written. You'll write on it just the same way we do quizzes. Questions on final exam, and I'll be doing. If questions come up, I'm happy to answer them at that review session. All right. So let's jump right into some practice. And I'm going to encourage you to do this on paper just like you would on an actual exam. Here, we're giving you a class, or we're telling you that we want you to implement a class named staff. And we're giving some description and some example usage. And I'm just going to leave it at that and let you all take it away from here. And we'll spend like 10 minutes on this. For folks who are remote, if you finish up, click the plus sign on the message just posted in Course.Care. Another couple minutes on this, and then we'll work through it together. If you're done, I would encourage chatting with your neighbor to convince yourselves you have the same return type for the greet method and how you're able to discern what that return type is. One more minute on this. All right. So when you see a prompt like this, we're trying to ask you to infer some of the details and figure out, given some usage and a little bit of description, how can you figure out what's going on behind the scenes in order to make this usage come to life and be possible? So when you read this, the class's name is staff, okay. The two attributes, name and isCS, okay. You should be able to construct a staff object with a constructor that has those. Okay, so that's what's going to make this constructor call work. And we know that this is going to be the name. This is going to be the isCS Boolean. and implement any methods necessary. So, okay, we're going to have to think a little bit more closely about our methods. Here's one method call. Here's another method call. They're named the same things. When you're looking at a method call, you're trying to discern what parameters does it need. In this case, it's only going to need the self parameter because every method needs that, but it's not going to have any additional parameters. And then you got to figure out the return type. Well, okay, so we see that when we print the result of calling this, it's not printing none, right? It's printing a textual value. So that means it must be returning a string. So greet must return a string. And there isn't going to be a print statement inside of the greet method. So let's start with the easier two things, the attributes and the constructor. And when I define my class, we use the keyword class. And staff is the name. And then we have our attributes. So name is a string, and is CS is a Boolean. And then we have our constructor, which is the special double underscore init, double underscore, self. And then we have the two attributes that we're going to be initializing as parameters. So name stir is CS bool. And I'm getting that colon just barely in the margin there. And then our constructor is going to do what most of our constructors have been doing in the past. So self.name is assigned name, and self.isCS is assigned isCS. We could have named our parameters differently if we wanted, and that would have been fine as long as our attribute names matched what was expected. But here we're seeing, the makeup of a constructor. It's got this special name. It's got this special self parameter. And we don't type self, right? If we did type self, it would be self is of type staff. But we never do that because we always know self is the same type as the class it's being used in, right? And otherwise, this is a pretty straightforward constructor. Questions on what we're seeing here so far and how we would know that this is how we would set it up. All right. So now we need to think about this method. And before we worry about the implementation of the method, with detail, we can try and discern what is the signature of it. What is our definition line going to be? And we already kind of thought through this. So we know that the name is going to be greet. We know that it's not going to have any extra parameters, just a self parameter. And we know that it's going to return a string. So we can define that method named greet. And it has a self parameter. And it returns a string. Right? On a quiz or the final, and all we have left is the final, so on the final, you don't need to worry yourself with doc strings in code listings if you don't want. We're mostly focused on the implementation here. So the implementation of this, okay, now we need to go and look and see how does this work. Well, in one case, we're seeing, hello, I'm Chris in CS. And that's the case where the staff object had isCS established as true. And in the other case, when we call greet on the doctor object, it says, hello, I'm Mara, not in CS. And that's a different output, or a different return value, I should say, because the false of isCS was established as its attribute value. So it looks like we can test on the isCS attribute value. So we can say if self, I'm actually going to give myself just a little bit more space here. So if self dot is CS. I'm going to come back and talk about this in just a moment. Then what we're going to do is return f string. Hello, I'm self.name in CS. Else, return f string. And there are other ways we could have implemented this. We could have set up a string variable to concatenate to, and we could have only concatenated differently once we hit the self.name part. I'm just doing it this way because it's the shortest in terms of the number of lines. Hello, I'm self.name, not in CS. And I'm just going to wrap that around to the next line. All right? Oh, let me get this camera out of the way real quick. Sorry about that. Cool. Questions on, yep.
So are we assuming that the default for the isCS tool is true, and that's why we don't say like if self.isCS equals true?
Great question. So the question is about this line right here. And the question is, do we assume that self.isCS is true? And that's very close to the way to think about this. But let me try breaking this down in a slightly different way, which is if we wrote if self.isCS equal true, this can work as well, but I want to show you why we don't have to do this. So what we know about when we reach an expression, and this is an expression, it's an equality operation that's happening. We're testing is CS equal to true. But this has sub-expressions, right? So this is one sub-expression that's just a Boolean literal, the value true. And this is another sub-expression that's an attribute access, where we're saying, go look up what is self.cs. So let's start with the example of this prof object. We initialize it with an attribute is CS true. So the first thing that would happen is the processor would say, OK, if true is substituted there, and that would be is equal to true. And ultimately, this would establish, this would simplify down to if true, then we go into the then block, right? Now, if we thought about it with the other object, it would have been false here. And if false is equal to true, this would have been false. So this is like saying if false, right? And we know that when that happens, we would go into the else branch instead. So what I want to convince you of, we don't need that test when we're dealing with a Boolean value, right? Because if we think about how does this simplify, well, first we go look up what is this expression. Well, on the first object, that would have been true. And we're saying if true, go into the then block and continue there. But with the second object, this doctor object, where we initialize that to be false, and we looked up what is self.iscs, it would have said if false, and that's what would have caused us to go into the else branch instead. And so there's nothing inherently wrong with saying if some Boolean is equal to true, but it is redundant because the Boolean itself has to be either true or false. What kinds of return types would result in none when printing the function call? Well, the none return type would. So if you had a function like def f returns none, and you just implement it, you can actually, I'll talk about these ellipses in just a moment, but now's a fine time. These three periods after one another in Python is a valid expression that just means do nothing. It's called a non-operation or a no-op in computer science. And so if we printed somewhere else the result of calling f this function and it had specified a return type of none, we would have seen none printed out. And I would encourage trying that. Let's see, any other questions from online? Do we need this stir method before defining the greet method? Good question. So we talked about the special magic method like stir. You'd only need to define this in an example. This is a great question. If we tried to say print, doctor, and we didn't call any method on it, then we would, and we still had this output, you would have imagined, okay, rather than naming this greet, we would have wanted this method to be named stir with double underscores around it. When it comes to, I will say though that when it comes to implementing classes, and we ask you to do exercises like this, we're not gonna have that level of implicit, like we're gonna make everything very explicit. Here, you're remembering the detail of needing to write that method, and it's true you would need to, but if we ask you to do this on the final, I can give you some ease to know that, like, if we ask you to implement a method, we're gonna show you a method called toIt directly, not implicitly behind the scenes using AutoMagic or even operator overloads. Other questions? All right. Cool. So I'm actually going to skip this diagram, and I want to change this just slightly based on my experience in the previous section. We're going to do a little bit of live modification to a code listing here. One sec while I decide. All right. I'm going to change two things really quickly that will make this a little bit easier. So this print statement is going to be A, and then we're going to substitute A, and then L, and substitute L. All right, we're going to ignore this line, and we're going to ignore this line and do the same thing here. So this is going to be dash L, substitute L, and this will just be A. All right, so what's happening here, the changes that I'm making to this are that we're going to have one print statement branch when we go into this function, and then when this print function is reached, we're going to print A, and then substitute the A parameter, and then L, and substitute the L parameter, just so we keep track of that. And then after this if-else, we're going to print that same thing, but this A is going to be increased. We're going to add 180 to just the print statement's output. We're not mutating anything. And otherwise, I think that's a good modification and gets us a point of getting started together. So to get this started together, we're going to have our globals frame. We're going to have a branch function. That's on lines 1 through 12. And we're going to have two variables in globals, a length variable and an angle variable. All right, so this length variable is initially 8.0, and the angle is initially 90.0. And then I'm going to give myself my entire column here for output. There's going to be a decent amount of output in this example, so I'm going to give myself just a bunch of room. And it turns out in this example, we're not going to have much happening on the heap. The intuition for why we're not going to have much happening on the heap is you'll notice we don't have any objects, we don't have any dictionaries or lists. And so this is just a recursive function call that is setting up frames on the call stack, or a recursive function that will be setting up frames on the call stack as it's evaluated. I'm going to give you all some time to try thinking through this. And what I want to point out is interesting and special about this particular listing is notice in this else branch, we've got two recursive function calls we're going to have to deal with. You're going to fully process one before you move on to the other. Okay? Additionally, in this case, nothing's happening. So if L is less than 4, we don't do anything. We skip past the else, and we just go and print. All right, so let's spend a few minutes trying to work through this example. And while you're doing it, what I'll encourage you to imagine is each time you call this function, imagine you're a turtle and you're moving forward by some L amount and you're turning to face the angle A and then moving forward by the L amount. And the angle 90 would be straight up. So in this first call to branch, you would be moving straight up 8 units and then turning 90 units. But I'll go ahead and allow you to keep trying to trace through this and try and feel the beauty of this recursion at play. I'm going to add the first 2 lines of print just to try and make it very clear. I'm not going to add my frame yet, so this is getting a little bit ahead of the frame setup, but it would say branch. Actually, you've got it, compare with your neighbors. If you're confused, try talking through it with your neighbors, maybe asking a TA for some help. A few more minutes on this one. This one's a challenging recursive diagram. One more minute, and then we'll talk through this one. All right. It's okay if you didn't get to the end of this one. It's also okay if you got a little tripped up at tracing through this dual call, or if potentially this tracing a recursive procedure that returned none threw you off, because these are two things we haven't done yet this semester. And they're beautiful. All right, so let's see why it is that this is just such a beautiful code listing. So I've gone ahead and set up my frame for branch for this call, right, where we're passing in the length and the angle, 8 and 90. In this function definition itself, I'm abbreviating those parameters just so there's a little bit less writing in our diagrams. L is for length, A is for angle. And I went ahead and reached line 2 and 3 to print out those two lines. Then we reach this conditional, and we test if L is less than 4. Well, L is 8, so that's false, right? So what do? Well, we go to the else branch, and here we reach a function call. What I want to remind you of is, even though this is a recursive function call, all the same rules apply, no different than if this were a call to, say, like a function named foo, right? If there's some other function named foo, we would set up a frame for it, we would jump over to that function, start from the top of it, and then come back with after it's done and returned. We're going to do the exact same thing for our recursive call. It's just feels a little bit weird because it's within the same function itself. But all the same rules apply. So we're going to set up a new frame here. And the frame is going to be named branch. This time around, we've got two different parameter values. So we'll compute those in just a sec. And our return address is line 9. And this example is why we keep very specific track of our return addresses. Okay, so what's L going to be? L is going to be one half of the L in the frame we're coming from. So 1/2 of 8 is 4. And A is going to be 90 plus 45, which is 135. All right? So we jump into this frame, right? So after you set up a frame, by establishing its return address and its parameters, you jump in, and you go back to the top of whatever function that you're calling, right? We're calling the branch function. So after we set up the frame to let us start processing this branch function call, where L is 4 and A is 135, we go back up to the top, and here's where we're going to print branch again. All right, so branch gets printed. And then we print the line where A is, in this frame, 135, and L in this frame is 4.0. All right? So then we reach this conditional again. We test, is 4.0 less than 4.0? No, they're equal to one another. So we go to the else branch. Uh-oh, we've hit that same recursive function call again. Let's go process it. Again, the same rules apply. We reached a function call, so we set up a frame for it. The next frame that we're about to jump into has a return address of line 9, has an L value parameter of half of 4, so half of 4 is 2.0, and an angle of 135 plus 45, which is 180. We've set up our parameters. So what we're about to do is change frames. So now the frame that we're working in is the frame where L is 2 and A is 180. And we jump back up to the top of this function definition. All right? Okay, so we go process this recursive function call. We print branch again. A, in this case, is 180. And L is 2.0. All right, that's the second print line that happens. And here we finally, in this call, reach a base case. And in this base case, L less than 4, well, the current frame we're working in is the lowest on the stack that is yet to return. L is 2, so this is true. What do? We do nothing. We skip over the else branch, and we just print this statement. We just print this output. So A is not 180, it's 180 plus 180, which is 360. And L is still 2.0, all right? So we just finished line 12, and here, notice we're reaching the end of a function that returns none. So the end of a procedure has an implicit return statement where our return value is none. Okay, so our RV here is none. And we return back to line 9. So line 9 was this line. This call to branch just evaluated to none, so this line is completed, and now we're about to begin processing line 10, where we see another recursive call. I'm pausing here. Before we go evaluate this line, we still got more work to do, so we're definitely not done with this yet, to see if there are questions on how we got to this point. So we got to the bottom of, we hit one base case, and that's return. But now we're seeing a recursive function that has 2 recursive calls in it, and we need to go recur with this other set of arguments instead, okay? So let's set up another frame. So we set up a new frame, like we will with any function call. Branch, return address is line 10 this time, because we're calling, notice this is the line that we've reached this recursive call on. And L this time is a quarter of what? Now here's why we always say the current frame, so we're setting up this frame, we're not yet jumping into this frame. So what is our current frame? Our current frame is the lowest one on the stack that is yet to return, right? It's the frame where L is 4 and A is 135. So when we're figuring out what is L multiplied by 0.25, we're asking for what is a quarter of 4.0, because this is our current frame. And a quarter of 4.0 is 1.0. So the L parameter of this new frame we're setting up is 1.0. And then we're saying, okay, subtract from 135, 45. And that's going to be the A, or the angle parameter. And so that's going to be 90. Okay? And that frame is now set up. So what are we going to do? We're going to jump into that frame. So now the current frame is the frame that we just established. We finished establishing it. You're done establishing a frame as soon as you set up its parameters and its return address. We go back up to the top, and what we're going to do is we're going to print branch again. And this time around, A is 90 in our current frame, and L is 1.0. Okay? Then we reach this if L is less than 4.0. Well, this is the frame we're in. L is 1, so 1 less than 4 is true, so we don't go into the else branch. Then we're once again printing, A, which is 90 plus 180 is what we're printing in this substitution. So that's going to be 270. And L is going to be still 1.0. All right. We reach the end of this call, so our return value here is none. And here's where things get interesting and where we have to be very careful. All right, so this frame just finished, and we go back to line 10. This is the line that we just finished. And now the question is, well, which frame are we back in after this line finishes? Again, we're always in the lowest frame that is yet to return. So the frame that we're in is this one here. And we know that because notice there's no return value, right? So we just finished this line, nothing else to do. And now what we're going to do is we're going to print A, and we're going to add 180 to A. So A is 135. It's very stressful to do math in front of, very basic math in front of an audience. Okay, so 315 is what we're going to print. So we're printing A 315 and L. So what is our L? Our L is 4 in the current frame, right? So we look up what is L in this current frame. L is 4.0. Cool. And we've reached the end of this frame, right? So now here is where I promise you, if you're trying to do this in your head, first of all, good luck. But even if you're writing all this output down and kind of keeping track of that, good luck remembering where you would go back to at this point. But this is why we have the stack, and the stack is keeping track of where we go back to. So notice our current frame, the one that we're reaching this line 14 in, is this frame where L is 4, A is 135, and our return address is 9. All right, so what we do is we go back to line 9. This was the call we just completed. And now the next thing that we need to do is go to line 10, but we enter our return address here, or sorry, our return value, return none, to line 9, so that line's done. And now we're back in the first frame that we set up, right? So we're almost done with this. But in this frame, L was 8 and A was 90. So we need to call this function one more time recursively, right? So this is a pretty wild recursive process. We've got multiple recursive calls in a given frame. So here, what is a quarter of 8? That's going to be 2.0. And what is A minus 45? That's going to be 45.0. Right? So our last frame to set up here, branch L is going to be 2.0. And A is going to be 45.0. And our return address is line 10. All right, so we've set up our frame. We go to the top. We once again print branch. And then we print, A of our current frame. Our current frame is no longer, this one is the lowest frame on our stack that's yet to return. So it's this frame. A is 2.0. Oops, sorry, A is 45.0. And L is 2.0. And we test is L, which is 2 less than 4, that's false, so we go to the else branch. Or sorry, L 2 less than 4 is true, so we do not go to the else branch. And then we reach this print statement. So we print, once again, A is 45 plus 180, so that's going to be 225. And L is still 2.0. And we reach that return statement, or the implicit return statement. We return none. We go back to where? We go back to line 10. We just finished line 10, but our current frame is this one here, right? The frame where L, the original frame, L was 8 and A is 90. We just finished line 10, so all that's left to do to complete that function call is print A of 90 plus 180, so 270, and L of 8. Right? We reach the end of that. This frame returns, and we're done. Right? So this is a pretty involved recursive process. Do you see how beautiful it is? Do you see what we're doing here? Do you not feel the power and the artistry here? So did you imagine what it would look like if we traced out an angle of 90 degrees? So let's just try this real quick. So we trace out an angle of 90 degrees, a length of 8, right? So we'll call that 8. And then we trace out an angle of 135 degrees, but only 4. And then we trace out an angle of 180 degrees, but only 2. But then we go back. So we go back to where we came from, and then we trace out an angle of, so that 360 degrees was moving back in this direction. And then we trace out 90 degrees, so we're going up 2, and then back 2, because we're going down 270. And then we go to 315, so we go back to here. And then we go to 45. And then we go to 225. So back. And then we go back to 270. The beauty. Like, look at that. It's beautiful. Do you all really not see? All right. We're at the point in the semester where I think what we need to do is close our eyes for a moment and take a pause. So everyone close your eyes. And folks who are on Zoom, close your eyes as well. Let me show you how dark it is in this classroom. That's the classroom view. And I want you all to take a deep breath. And imagine you're in a lovely forest among the trees, full of nature and recursion. And exhale. Don't forget to breathe. I'm not a trained breathing certified specialist, so breathe when you want, whatever feels comfortable and relaxing. And just imagine all these happy little trees. There's not a final in sight, even though they're only a week away. But we're among the trees right now. We're present in the moment, not worrying about what's coming. And we're visualizing the beauty, the absolute beauty of that recursion that just came before us. And so if you can't visualize that beauty, well, I haven't done my job as a professor, so I'm going to turn it over to a friend of mine to try and give you a different explanation of it. And so what we're going to do now is we're going to jump into VS Code. You can open your eyes, pull out your computer, and we're going to jump into VS Code. And what we're going to do is we're going to make some happy little trees together. You may know me from my appearances on YouTube. I'm Bob Ross. And yeah, let's paint. So I'm going to have you join me in VS Code. We're going to make a brand new file. Let's do this in lessons. And call it Happy Trees. Yeah, that other professor, Chris, he tried to show you the beauty of that stack diagram, but let's actually see the beauty and make some art together. So we need our paintbrush, our trusty tool, the turtle. And we're going to import this turtle as T, which is an alias. So this is going to be a little bit different than we've done it in the past, but we'll be able to say T.forward, and we'll move the turtle forward, things like that. Why don't we go ahead and just at the sort of bottom of our code, set up call it a done. And what this call it a done is going to do is it's what causes the screen to show up in our program to actually run. And we'll add some more things to the bottom. But let's go ahead and set up we're trying to paint a tree here. And we probably want to paint a tree somewhere on our canvas. So we'll set up some coordinates that we might paint this beautiful, lovely tree at. All right? And we can add a docstring here as in good measure. Paint a beautiful tree. So the way that we're going to do this, we know how a turtle works, right? It's like being able to make a stroke on canvas, but we need to move our turtle to the correct place before we do anything else. So we'll say t.pen up. So we're not going to drag our paintbrush around. We're going to move it to the xy coordinates that this function call was given. And then we're going to put our pen back down. We're ready to start drawing. All right? So how do you draw a tree? Well, why don't we start with a branch? That'll be our trunk. All right, so why don't we set up a constant here, such as trunk length is 100.0, and angle is 90. So our trunks usually grow. We're going to say that in this happy little painting, our trees are going to start 90 degrees vertical straight up. And then we're going to branch. And we're going to give this branch function the trunk length and the angle we want to paint it at. OK. So now we need a branch function. And we need this function to have a length parameter of type float and an angle parameter also of type float. This is also going to be a procedure. Paint a beautiful branch recursively. All right. And so here's where we really get to have some fun. What we want to do is set our turtle in the right direction. We have an angle here, so we want it to be pointing up, so we're going to set its heading to this angle. And then we want our branch to move in that direction. T.forward, a command you probably remember by this length. Well, when we're painting, not only do we tend to stroke up, but we might want to stroke right back down to where we came from. And this will be important when we start actually trying to draw the branches of our tree, like we did in that previous little illustration. So what we're going to do is we're going to set our heading back in the opposite direction of the angle that we came from. So angle plus 180 degrees, right? So 180 degrees is a half spin, so this is going to turn the turtle back in the opposite direction we started, and then let's go back to where we came from by moving the turtle forward by that length. Wow. I know you all can already feel the beauty of this painting that we're making together. So let's see what this looks like. Let's see how our art comes together. So I'm going to run python-m lessons.happytrees. Uh-oh. You know what we didn't do? We never called our tree function. We just said done. We defined two functions. That's art, really. So tree 0, 0 is how we can kick this out. And let's make these floats to be precise here. All right. So start at the origin, which is the center in our turtle graphics of the canvas. And wow. Can you see how beautiful that trunk is? That is the finest trunk in all of the lands. So we have a little bit more work to do. We need to make some branches. So when you have one branch, you kind of want to have another branch coming out of that branch, right? But it probably turns a little bit and gets a little bit shorter. So here's where our recursion comes into play. So we have this notion of if length is, at some point we need to stop recurring. So if length is, say, less than 3.0, we're going to do nothing. This is our base case. It's a weird base case. And it's one that there are ways that we don't necessarily have to specify, but I do think we have, I do think it's good practice when you're getting comfortable with recursion to try and specify your base cases recursively, and this is us doing that. So the recursive case then is saying, okay, well, let's branch again. We just finished one branch, let's go start another one. But let's make it a little bit shorter. So maybe the length parameter that we assign is the current length multiplied by, I don't know, 65%, right? So we're going to shorten the branch, and then let's maybe turn it by, actually, let's make it 75%. Why not? What the heck? And maybe make the angle, I don't know, 25 degrees more to the left, or more clockwise, I should say. All right. Let's go see what our beautiful tree looks like now. Our happy little tree. Oh, there's that turtle. Oh, look at it. Oh, it's coming up. Wow. It's almost a really beautiful tree. It has the promise of something really great, but it only branches in one direction, right? It's not quite a happy tree. It's a sad little tree. So how can we make this a little bit happier? Well, why don't we add more branches? So we can branch in the other direction. And let's make this maybe, I don't know, 70%. That sounds pretty. The length of the current branch. And an angle of, say, we're going to turn counterclockwise this time. I don't know, 23, Michael Jordan's number. Why not? So we're just making some art together here. And here's where the magic and the beauty of that last example that you all just traced through painstakingly in an environment diagram really shows up. Wow, that is a busy, this is a little bit too slow for me. It's a busy turtle, but you can kind of see what's going on. Every time that turtle is changing directions, a new frame is being added to the stack and being processed. When it goes back in the same direction it came from, that frame is being returned and it's moving back. And wow, it's really trying pretty hard, but let's make this a little bit faster. We can do better than this. So t.speed, 0. The fastest speed. This turtle is going to be running around our canvas, right? Oh yeah, that's a little bit better. And so what I want you to appreciate in this is that we're seeing the recursion that we implemented actually visualized live as each one of these lines is being traced out. And notice that every single call that doesn't wind up in the base case is resulting in 2 more function calls. And so this is where we have effectively exponential growth, where we're doubling each time we call a recursive frame that doesn't lead to the base case. We're doubling the number of frames that we're going to have in our stack. And so we've got a really intricate drawing coming together. This is still taking quite a bit of time, but it's still incredibly fast compared to how long it would take to imagine trying to diagram this by hand and what's going on in memory, what we just did. The same steps are happening. If you compared this to what we just traced, it's effectively the same with some of the constants changed around. This is still a little bit too slow, so why don't we do one more magic incantation, and then we'll try and actually paint together and make it a little bit more interactive. So there's some magic things that we can do in Turtle. We can use this tracer function, which says don't update until t.update is called. So it turns out there's a way that we can, why it's as slow as it was for each of those lines is because we're artificially slowing it down so you can see the animation. This override, which you all may have used in the Turtle art, is going to allow us to just carry out a bunch of function calls, and then we have to explicitly tell the Turtle when to update the screen. So that's saying don't update the screen until t.update is called, and then what we need to do is up in our tree function, so I'm going to try and leave this scrolled down. I know I'm moving a little bit fast here, but we're just painting together, and this will all be recorded online. After we call branch from within the tree function, add a t.update method call. or technically this is a call to a function in the module. And that's what's going to cause our tree to paint. So now we try running our program. Boom! Look at that beautiful tree. And that actually is pretty impressive when you think about the generation of this art, frankly, that came from, 33 lines of programming. A very clever 33 lines, but nevertheless artistic. And so, okay, we said we were going to paint together. I don't know if any of you all played with this when you did the turtle library, but there's another cool thing we can do, which is, it's kind of boring to draw a tree at the same place every time this program runs. So rather than calling tree, why don't we make it so that we can click somewhere and call tree where that click happens? So we can say t.getScreen. And what this is doing is it's giving us back an object that represents our window that has some other methods defined on it. And we can ask that object, the screen object, to do something every time there's a click. What we wanted to do is call the tree function, right? So this is what we would call a higher order function, where we're saying, hey, on click, every time you click somewhere, I want you to call this other function, and this will work as long as that function expects an xy coordinate. All right, so let's go try this out. Wow, we can paint ourselves a happy little forest here, and that's pretty great. So we could play around with this a little bit more. Nature is not deterministic in the way that our program is, so we could add some non-determinism if we wanted. We could import random from random. From random, import random. So from random, import random, not the other way around. So from the random library, we are importing this function named random. When we call random, we'll get back a floating point value between 0 and 1 at random. So why don't we add some nature to our program? So nature is a floating point that is random. And let's say we're going to change our angle by nature amount. So maybe we multiply this random percentage, effectively is one way of thinking about it, a random percentage between 0 and 100%, multiplied by, say, 20 units. And when we branch the first time, let's maybe be a little bit more, use nature to our advantage here, and maybe add on 5 plus random. I don't know. We're making art together. We're going to see how this feels. Oops, 5 plus nature. And then maybe for the other branch, we subtract 5 plus nature as well. So, nature is now in our program. It was just Earth Day. Why not? And I have no idea how this is going to look. It might look terrible, but let's see. So, hey, wow. Those are actually looking kind of nice. And if you were to compare these trees, there's still similarities, like the lengths. We could have made some of the lengths random instead of deterministic. And you could imagine playing a little bit more around with this as well. And we have some happy little trees. Recursion can be used to process lists in just the way that you've been doing in this latest exercise. You'll learn in the next course that you can have tree data structures where your node can be connected to multiple other nodes, which can be connected to multiple other nodes to form trees. And the way that you could imagine an algorithm that's recursive going and processing those trees is very similar to this. So there are just a few notes I want to make to close out now that Bob Ross has graced us with his presence here. Nope. I'll post these slides after class. There's actually a really cool tool that you can use to practice and make some recursive art online that's fun to play with. At the beginning of the semester, we spent some time thinking about this fundamental pattern in computer science, right? Some inputs are fed into an algorithm that generates some expected result, hopefully. And all of this is happening with within some kind of environment. You've seen this come to play in many different stages of the semester where you've written functions that take some inputs, return some value, and maybe they impact the environment in some way. Maybe you're reading in from a file that exists on your computer and processing some data. Maybe you're playing a game like Wordle and just trying to output the state of the game. And we've written a lot of programs along this way. But this pattern applies to other things, and I think maybe some of you have figured out that the way we try and structure this course is you're an input to COMP110. And the COMP110 algorithm pushes you really, really hard, right? There's a bunch of exercises in a given semester. There's a lot of videos to watch with homework and lessons to complete on Gradescope. There's a lot of time we spend together in lecture diagramming. The quizzes are always a bear to get past, and we still have a final to come yet. And this has all been happening within the context of a continued pandemic. And some times of this semester, it's felt like we were kind of in the clear. Towards the end, for a minute there, it turns out we weren't. And we're back into, we started the semester with a wave. We're kind of ending with a wave. And just getting back acclimated to campus is a real challenge on top of everything else. And so you all have risen to the occasion. But what's I'd like to impress upon you and ask you to reflect on is the fact that in this process, you can now call yourself a programmer and a data scientist. You've done the work to become confident and capable as programmers and data scientists. And that's no small feat. This is a very challenging course at UNC. So before we close, I want to give special thanks to a couple groups. The first group, and if the folks who are here from this group would stand today, so the Team 110 is stand-up TAs. Round of applause for you all. So we had a lighter crew in today because it's our weird Tuesday, but these folks have really, as you know, carried the course from start to finish. They host office hours, which we've had over 4,000 one-on-one appointments this semester. They host tutoring, review sessions, they help print quizzes, they help scan and grade quizzes. They completely run Hack 110. The website design is entirely done by the team, the contents and the resources and all that. Really, so much of this course wouldn't be possible. The course, in fact, would be impossible without these folks. And so, yeah, thank you all. And I'll take this as a note to also encourage those of you who are interested in applying. We've got 2 seniors whose spots will be open who have been on the team for multiple years. And yeah, it's sad to see seniors go, but always fun to bring in new members of the team. And then finally, I want to give a special thanks to you all for such an amazing semester. You all have put in a ton of hard work. The team's been really impressed with the energy you brought to 110 this semester. We've tried some new things. We've done things a little bit differently, and you all have rolled with it. So a round of applause for you all as well. And that's it. We're done with the semester in lecture. We'll see you for the final exam. Great work, everybody.